In this video, I'm going to break down everything you need to know about NASA's Artemis II mission. We are going to cover the spacecraft, the mission profile step by step, the 4 crew members, and what comes next for the Artemis program. By the end of this video, you will have a complete picture of what just happened and why it matters. Let's start with the basics. Artemis II launched on April 1st, 2026, from Kennedy Space Center in Florida. It carried 4 astronauts on a 10-day journey to the moon and back. It was the first time human beings have traveled beyond low Earth orbit since Apollo 17 in December 1972. To put that in perspective, for the past 54 years, every single human being who went to space stayed within about 400 kilometers of Earth. The International Space Station orbits at roughly that altitude. You can actually see it pass overhead on a clear night with the naked eye. Artemis II went much, much farther than that. At its maximum distance, the crew was 252,756 miles from Earth, which is 406,771 kilometers. That set a new record for human distance from our planet, breaking the previous record set by Apollo 13 in 1970. But before we get into the mission itself, let me explain the hardware, because understanding the spacecraft is key to understanding how the mission worked. The rocket that launched Artemis II is called the Space Launch System, SLS. It stands 98 meters tall, about the height of a 30-story building, and at liftoff it produces 8.8 million pounds of thrust. That makes it the most powerful rocket NASA has ever launched. To give you a sense of scale, that is roughly equivalent to 13 Boeing 747s, all running at full throttle at the same time. The SLS has 3 main sections. At the bottom is the core stage, which burns liquid hydrogen and liquid oxygen. Attached to the sides are 2 solid rocket boosters, each one 54 meters long. Those boosters provide about 75% of the total liftoff thrust for the first 2 minutes of flight, then separate and fall into the Atlantic Ocean. On top of the core stage sits the Interim Cryogenic Propulsion Stage, ICPS, the upper stage that performs the translunar injection burn, which we will get to in a moment. A common question is how LES compares to the Saturn V rocket that sent Apollo to the moon. The Saturn V was actually taller, 111 meters, and could carry more payload to the moon, 45 metric tons, compared to 27 metric tons for the SLS Block 1. So why build a new rocket that carries less? The answer is in the design philosophy. The Saturn V was purpose-built for Apollo. It was designed to be used once and discarded. The SLS is designed as a long-term, flexible platform that will support the entire Artemis program over decades, with upgrades planned for future versions. Now, sitting on top of the SLS is the spacecraft itself, Orion. Orion is made up of 3 parts, the crew module named Integrity by the Artemis. 2 crew is where the 4 astronauts live and work. It is 5 meters wide and provides 9 cubic meters of habitable volume. That is about 50% more space than the Apollo Command Module. Below the crew module is the European Service Module, ESM-2. This was built by Airbus for the European Space Agency, and it is the part of Orion that provides propulsion, power, thermal control, and the water and air the crew needs to survive. It is a critical international collaboration, and without the ESM, the mission does not happen. At the very top above the crew module is the launch abort system. If something goes wrong during launch, the abort system can pull the crew module away from the rocket in under a second. It is the crew's last line of defense if there is a catastrophic failure on the pad or during ascent. Now, before we get to the mission timeline, I want to explain something that almost delayed Artemis II by another year, the heat shield. When Artemis rover, the uncrewed test flight in December 2022, Returned to Earth, engineers examining the heat shield found unexpected erosion patterns. The heat shield on Orion is made of a material called coat, the same material used on the Apollo capsules. During re-entry, the shield ablates. It burns away in a controlled manner, carrying heat away from the spacecraft. The problem was that the erosion patterns did not match what the computer models predicted. For an uncrewed mission, that was acceptable. For a crewed mission, NASA needed to understand exactly what was happening before they could certify it as safe. The investigation took 18 months. Engineers discovered that the manufacturing process had trapped small pockets of gas inside the coat material. During re-entry, those gas pockets expanded and caused localized chunks of material to break away rather than ablating smoothly. NASA redesigned the manufacturing process for the Artemis II heat shield. On April 11, 2026, when Orion Integrity re-entered the atmosphere at 24,661 miles per hour, the heat shield performed exactly as designed. Chapter 2. The Mission, Step by Step. Launch day was April 1, 2026, Kennedy Space Center Launch Complex 39B, the same pad that launched Apollo 10 in 1969. One thing worth explaining here. When you watch a rocket launch, you will hear two different countdown clocks. The L- clock counts down from the start of launch preparations, which can begin days before liftoff. The T- clock is the terminal countdown, the final hours and minutes before ignition. At T-0, the engines ignite and the hold-down arms release. At T plus 2 minutes, the solid rocket boosters separate and fall away. The core stage continues burning for another 6 minutes, placing Orion into a parking orbit about 185 kilometers above Earth. The crew then spent the first 24 hours in high Earth orbit, systematically checking every system on the spacecraft. Life support, propulsion, navigation, communications, everything gets verified before they commit to leaving Earth's neighborhood. This is the critical go or no-go phase. If any system fails here, they can return to Earth safely. Everything worked. At approximately T plus 24 hours, the ICPS performed the translunar injection burn, known as TLI. This is the engine burn that sends the spacecraft from Earth orbit toward the Moon. It lasted about 18 minutes, and when it was complete, Orion was traveling at approximately 36,000 kilometers per hour. Now, the trajectory chosen for Artemis the Sin is called a free return trajectory. This is worth understanding because it is one of the most elegant concepts in orbital mechanics. A free return trajectory is a path through space that uses the gravitational fields of the Earth and Moon to naturally guide the spacecraft back to Earth without requiring any additional engine burns. If the engine fails completely after translunar injection, the spacecraft will still fly around the Moon and return to Earth on its own. The physics of the trajectory guarantee it. This is not a new concept. Apollo 8 used it in 1968. Apollo 13, the mission that suffered an oxygen tank explosion in 1970, survived partly because of this trajectory. When the explosion disabled the service module, the crew could not use the main engine, but they did not need to. The Moon's gravity bent their path and sent them home. Artemis II flew the same type of trajectory. On April 6, 2026, 5 days after launch, Orion Integrity reached the Moon. The spacecraft passed 4,067 miles from the lunar surface, and at maximum distance the crew was 252,756 miles from Earth. That broke Apollo 13's 56-year record of 248,655 miles. The crew spent approximately 8 hours in the vicinity of the Moon, conducting systems tests and running the onboard experiments. Then Orion's engine fired one more time to begin the return journey. 4 days later, on April 11th, re-entry began at about 400,000 feet above Earth's surface, with Orion traveling at 24,661 miles per hour. The heat shield faced temperatures of approximately 2,760 degrees Celsius, hotter than the surface of the Sun. The re-entry sequence lasted 13 minutes, At 24,000 feet, the drogue parachutes deployed. At 8,000 feet, the three main parachutes, each 35 meters in diameter, opened. Orion Integrity splashed down in the Pacific Ocean near Rosarito, Mexico, at approximately 1730 UTC. The USS John P. Murtha was on station for recovery. Total mission duration: 9 days, 1 hour, 32 minutes, and 15 seconds. Artemis II carried 4 astronauts, and each one made history. Reed Wiseman was the commander. He is a United States Navy test pilot, and he flew to the International Space Station in 2014, where he served as commander of Expedition 41. On Artemis II, he became the oldest person to travel beyond low Earth orbit. Victor Glover was the pilot. He is also a United States Navy test pilot, and he flew to the International Space Station in 2020 as the first operational pilot of SpaceX Crew Dragon spacecraft. On April 1, 2026, Victor Glover became the first African American to travel beyond low Earth orbit. Christina Koch was a mission specialist. She holds the record for the longest single spaceflight by a woman, 328 days aboard the International Space Station from 2019 to 2020. On Artemis II, she became the first woman to travel beyond low Earth orbit. Jeremy Hansen was the second mission specialist, representing the Canadian Space Agency. He became the first Canadian to travel beyond low Earth orbit and the first person from any country other than the United States to fly to the moon. 4 crew members, 4 historic firsts. While in deep space, the crew also conducted several experiments. Avatar studied how the human body adapts to microgravity in the deep space radiation environment, data that will be critical for planning longer missions. Archer monitored immunity biomarkers in the crew's blood, because space travel is known to suppress the immune system. LCRD tested optical communications using laser beams instead of radio waves, a technology that can transmit data 10 to 100 times faster than traditional radio, and that capability will be essential for future missions sending high-resolution data from deep space. Chapter 4. What comes next? Artemis II was a test flight. Its job was to verify that the hardware works, the trajectory works, the life support works, and that human beings can operate effectively in deep space for 10 days. Every one of those objectives was met. The next mission is Artemis III, and that one is a landing. Artemis III will put human beings on the lunar surface for the first time since Gene Cernan in December 1972. The landing site will be near the lunar South Pole, a region that contains water ice and permanently shadowed craters. Water ice matters a lot. It can be converted into drinking water, breathable oxygen, and rocket propellant. If you can make propellant on the moon, you do not need to carry it all the way from Earth, and that changes the economics of deep space exploration entirely. Artemis IV will deliver the first module of the Lunar Gateway, a space station in lunar orbit that will serve as a staging point for surface missions and eventually as a waypoint for missions to deeper space. The goal of the Artemis program is not just to visit the moon. It is to establish a sustained human presence there. Artemis II showed that the foundation is solid. The hardware works. The crew is ready. The next step is the landing. If this video gave you a clear picture of what Artemis II was and how it worked, subscribe for more, and let me know in the comments. Did you watch the launch live?